Hey, we're back for round 3 of Newton's laws of motion. Right now, what we're going to focus on is the application of those laws. So we're going to be working several examples. So go ahead and get your pen, pencil, calculator ready because we're going to get started. Okay, so here in this problem, we have a figure and it's showing a couple of blocks. We have one block that's sliding across the table. It has a mass of 3.3 kilograms. That's our big M here. And then we have a cord. Now you'll notice that we say that that cord is wrapping over a frictionless pulley. So that means we don't have to take that into account. That should probably clue you in that in the future, it's not always going to be the case. It's coming, just not for a while. Okay, it's going to be hanging. It's connected to this hanging block that has a mass of 2.1 kilograms. So the cord and the pulley, negligible masses, we can ignore them in comparison with the blocks. So we basically say, okay, in comparison, these are massless, so we can ignore their existence. Our hanging block is going to fall as the sliding block is going to accelerate to the right. Now we want to find the acceleration of block S. So how big is the acceleration that's going to the right? We want to find the acceleration of block H. So what is the acceleration of it that's going down? And we want to find the tension in the cord here. So let's get started. First things first, let's look at our free body diagram. So I'm going to look at mass M first, the big M. Now that has force due to gravity, so that's going to be big mg, and then it's going to have our normal force. Now the next thing it has, since we are on a frictionless surface, there is no friction, but we do have tension from that rope pulling to the right. So now when we look at this free body diagram, things that we should expect. Now, we expect that this mass in the y direction, we don't expect it to come floating off the table, and we don't expect it to be sinking through the table's surface. So we say that the net force in the y direction is going to be 0. That means force normal minus the force due to gravity is going to be 0. So that tells us that the two forces are equal in magnitude, opposite in direction. Now, in the x direction, our net force is going to equal the mass, which in this case is going to be big M, times the acceleration. So that tells me that the tension going to the right is going to equal the big mass times the acceleration that it experiences. So that tells me that basically our tension is directly connected to the acceleration of that mass. Now if I look at the little block, little m, I have just two forces. I have the force due to gravity on little m, and I have the force tension. So one thing I do know, since I have a common rope, that rope is going to have the same tension. It is a massless rope, so it's an ideal rope. So the tension throughout this is going to be uniform. So if I look at my net force, in the y direction, that's going to equal my mass, little m, times acceleration. So I have that the tension force minus little m g is equal to ma. So that tells me that my tension force is also connected to my acceleration of the small block. Well, that probably makes you wonder, well, how else could I look at this? I could look at this as a combined system, but the other thing I could do is I could substitute in. Okay, so I do have to remember to take into account that this is going down, so we have that negative sign here. So I need to group my a's together. So I'm going to have that negative mg is equal to negative big MA when I subtract that over minus little ma. So everything has a negative. So that means I can cancel all of those negatives. So I have little mg is equal to, I can factor an a out, big M plus little m. So that means I can find the acceleration of the system, because quite frankly, without breaking the rope, little m and big M have to have the same magnitude of their acceleration. So that magnitude is going to be equal to little m times g over the total mass of the system. So if we plug in our values, we are going to have 3.3 times 9.8 over 3.3 times 2.1, or plus 2.1. And so what we're going to end up with is about 3.8 meters per second squared. Now, from that value A, I can substitute in here and say, okay, well, my tension is going to be 3.3 times that acceleration. That works out to be about 13 newtons. So, let's keep going. In this example, we have a cord pulling a box of sea biscuits up a frictionless plane. Again, there's our favorite word, frictionless. One less force we deal with. That plane is inclined at 30 degrees. Now the box has a mass of 5 kilograms. We know the tension force. We want to find the acceleration component up the inclined. Okay, so first thing to recognize is right here what we have is a free body diagram of all of the forces. So we have our force tension here. We have our force normal from the plane. You'll note that these are perpendicular. Our tension is up the plane. And then we have our force due to gravity. Now, there's a couple ways we could work this. Sometimes we like to break and keep things along our normal x and y's, but here I have two forces, so I'm going to tip my axes so that this is a positive y, this is a positive x. That means I'm going to need to resolve my force due to gravity components and break this into a right triangle. So there will be a new force due to gravity in our supposed new y direction, and a force due to gravity that's in our new x direction. Now, if this angle is theta, and this is 90 degrees, this is 90 degrees, so by geometry, this angle right here is theta. So that means our new force due to gravity in our new y direction is going to be mg cosine theta. I know it's a y, but it's a cosine. That's because it's the side adjacent. We're dealing with a vertical angle. So the y is going to be mg sine of the angle theta. So how am I going to find the acceleration? Well, I'm going to look at the net force along that incline. So I'm going to look at the net force in the x direction. That should equal the mass of the box times the acceleration. So I'm going to have the force up the incline, so that's my force tension, minus the force down the incline, that's my mg sine theta, and that should equal the mass times the acceleration. So our tension is 25 newtons, our mass is 5 kilograms, our g is 9.8, we have sine of 30 degrees, which works out to be 1/2 if you remember your unit circle, and that's going to give me 5a. Okay, so when I take all of this and I divide it by 5, I'm going to get that my acceleration is about 0.1 meters per second squared, and that is my acceleration that is going to be up the inclined plane. So let's keep going here. So here we have a very familiar figure that is in an elevator. And so our passenger is standing on a platform in an elevator. And we are trying to read a scale. Now, what does a scale read? The scale is reading a normal force. So we are going to be looking at it when the car is stationary, when it is moving up, and when it is moving down. And so we want to find a general solution, whatever's happening with regards to the cab of the elevator. Okay, so first things first, we have that free body diagram off to the right side. So we are going to be using that. So if we look at this person in the elevator, their net force is going to equal their mass times their acceleration. Now, if they are going up, that acceleration is a positive value. If they're going down, that acceleration is a negative value. So this acceleration is not just a magnitude, it's gonna have a sign as well. So what do we know? Well, we know that the force normal minus the force due to gravity is going to equal the mass times that acceleration. So I want to find a general solution for the scale reading. Well, the scale is measuring our force normal. So force normal is going to equal force due to gravity plus mass times acceleration. Now that acceleration is a signed acceleration. I tend to try and put some sort of notation above it to remind myself that it is a signed acceleration. So this is going to be mg plus mass times acceleration. So what about if the elevator is 0, has an acceleration of 0? So if the acceleration is 0, then my force normal is just going to equal mg. Well, if that acceleration is upwards at 3.2, then my force normal is going to equal the mass times g plus 3.2. And I can get that value. If my acceleration is negative 3.2 meters per second squared, because I'm going down, then my force normal is going to be mg minus 3.2. So that acceleration is assigned. So here is our general, keeping in mind that it's signed, and then I can substitute in. So if I look at my mass times my gravity, just bare bones basic, I'm going to get here, I'm going to write that over here, so A equals 0. My force normal is going to equal my mass, which is going to be 72.2 times g, which is 9.8. So that's going to be about 708 newtons. So that's from this formula right here. Then if my acceleration is a positive 3.2 meter per second squared, my force normal using that base formula is going to equal my mass, g plus my acceleration, 3.2. So I'm going to have 72.2 times 9.8 plus 3.2. And so that is going to be 939 newtons approximately. If I'm going downward, my force normal is going to equal mass, g minus 3.2. So that's going to be 72.2 times 9.8 minus 3.2. That's going to be about 477 newtons. So what this is telling me is if you're going up in an elevator, the scale would read heavier than if you're going down, which makes sense if you think about how your stomach feels as you're going up and down in an elevator, because your stomach is a fairly good accelerometer. So take a gander at these. Let me know what questions you have.